I'll start recording the meeting. There we go.
Got it. Perfect. So it's all good now? It's recording?
Yeah, it's all good.
All right. So I don't know if any of you see me yet. I'm Liam. I go to Dalhousie in Halifax, and right now I'm taking computer science and math and statistics. And I'm working with Arthur here on the education side of things for the club. So today we're going to be looking at cryptography and consensus and what that is and how it's used in blockchain and all that good stuff. So generally we're going to go over what is encryption at all, what does it look like, and then we'll go over private key encryption to start off with, and then we'll talk about how that turns into public key encryption. And how public key encryption can be used to sign transactions. We'll figure out what that means. And then we'll put that together and see how that's actually all used in the blockchain as a whole. And then we'll move on to something that's a little bit different, but still tied into the same thing because it's all using hash functions still, which are a cryptographic function that you've heard about already, I think, from Arthur, but we'll go over that again. And then we'll talk about the different types of consensus mechanisms. So right now, they're proof of work and proof of stake are basically the two that are in use. All right. So first of all, what is encryption or cryptography? So basically, encryption is when we have a message, right, and we want to hide it. We want to make it so that we can send it to someone and people can look at what we're sending, but they can't tell what information that actually contains. And there are a lot of different ways to do it. And we use a lot of them in our different processes. So the first type we're going to look at is one you've already heard of, and is one that is used all across blockchain. It's not strictly speaking encryption because we can't actually decrypt it. So the hash function is a process where we take our input and then we hash it using a mathematical process. The process that Bitcoin uses is called SHA-256. It was developed by the NSA and released in like 2006 or something like this. And basically you put your string of any length into it, it chops it up, and it turns it into a unique 256-bit output. And you won't be able to figure out what the original input is just from the output. And what the advantage of this is that we can use for blockchain is that it's actually very easy to check if you have a correct hash. So say we have a message that we want to hash, and we do so, we get our hash. We're now able to check if this hash is the right one of this message by just checking once, right? We do our hash once. But if we want to find this hash and we don't know what the original message is, we're going to have to just, our only method, since we can't use this hash to decrypt, is to just guess and check different input strings. And we have to just keep going. And we're going to have no progress besides incremental piece by piece. And in order to be sure that we get the right one, we're going to have to guess all possible hashes, right? Which is for a 256-bit binary string, 2 to the 256. Which is a really big number, and you won't ever get there. So that's actually what mining is, right? Is we're trying to guess a hash with a specific number of zeros in front of it. We're trying to guess the string which we hash to get this thing. And we just guess and check. And then as we increase that number of zeros in our binary string, there's less and less correct solutions. So it takes longer and longer and longer to mine our bits, to mine our blocks, sorry. So that's not really an encryption function, but it is a cryptographic function that we're using in the blockchain. We'll talk more about that later when we get to consensus. All right. Second of all, now when we have encryption, we need to have a way to decrypt it, right? So we've got our hash function, which is able to take our input and encrypt it, but we're not able to decrypt it. And that's where the key comes in. So basically, single key encryption or private key encryption has been around for a really long time. It's where you have a message and then you use some method to make it impossible to read. So we could just, shift letters or something like this. We send it, and then the other person who wants to read it just uses that exact same key in reverse in order to decrypt our message. It's very simple and it's very easy to understand. I might actually have another slide about it. No, I don't. But it's not very secure because we need to actually get this key to the other person in order for them to be able to use it. And if we're using the internet, it's not going to be secure because we don't have it encrypted, right? Anyone who can see our original message is also going to be able to see the key that we use to decrypt the message, and our system is useless. So that's not good enough. We need something else. We need the second key. So this is the type of encryption that actually is used in blockchain, is actually used everywhere across the internet. It's called private key encryption. Or sorry, it's called public key encryption. Because when you only have one key, it would be called private key encryption. We add in the second key, which is called the public key, which I'll explain in a moment. Adds a lot of security. We call it public key encryption. And what this allows us to do is, here's our example here. We have Bob wants to send a message to Alice. And our encryption algorithm generates two different keys, right? And they're not similar, they're different. And they can't be figured out from each other, right? So just because we have the public key doesn't mean we can figure out the private key. So Bob wants to send a message to Alice, and we encrypt that message with the public key that we find for Alice. Alice gives us the public key in order to send her a message. We're able to encrypt the message. Now people aren't able to read it, and we're able to send it to Alice, and then Alice can use only her private key to decrypt the message. If we try and use the public key or someone else's public key or our private key to decrypt this message, it won't work. We'll get the wrong answer, and we'll be screwed, right? So it's not gonna work. But this isn't perfect. We still need something else for blockchain to work. We need to be able to verify who a transaction is coming from. And we're actually able to do that with this type of encryption as well, and be able to publicly verify it. We're able to do that by signing. So if we actually think about the way that these keys work a little differently, and we use them in the opposite order, we're actually able to ensure that a message that we're receiving is from an individual person. That's what his signature is called, and that's part of how it's used in blockchain. So how does that work? So basically we've got our diagram here. You can take a look at this. So say Alice wants to send a message to Bob, and they want to make sure that we know that Alice sent this, right? So this could be important because if you're sending a transaction to someone, you're saying, I'm sending you money, you want to be able to verify that like it's actually you that said that and it's not someone else, right? So we need to have a unique verifier that we're able to say that only Liam said that he was sending that money and it wasn't Arthur trying to spend his money. So the way that we do that is basically you take your message and now we can encrypt it with the private key, and that can be our signature. And now when Bob receives this message, he's not able to, he has the message. How does he verify that it's from us? Well, he can go to our public key and he can apply that public key to the encryption, to the signature, and see that it matches the message. Now, if you do that with anyone else's public key again, or with your private key, or with anything else, you'll get the wrong answer. The only way that you get the correct answer is by using the public key of the individual who sent the transaction. So that's actually very important, right? And now there are some issues. So this is our system. This is public key encryption. This is what encryption on the internet and everywhere that we use encryption is based on, and blockchain uses it as well.
Wait, what's the signature? Sorry to cut you off. Like, just wondering, like, the signature is not your private key, right? Because you're supposed to keep that private.
No,
it's not. And is there something that you randomly generate every time, or is it the same thing every time?
That's a good question. It is randomly. It's not randomly generated every time. So maybe I should explain this a little bit more. The signature is generated using your private key. That's why we're able to verify that it comes from you. Only you know your private key. That's when we talk about, the pros and cons of this, that's a very important part, is that only you know your private key. If anyone else knows it, or if it's shared on the internet or anything like that, the system is completely compromised. But since we know that only you know your private key, if we're able to have some sort of function which generates an output which is unique to your private key, then we're able to say that, like, you conducted this function. So what we're able to do is we're able to take this message, right, and hash it using the private key such that when we check it with the encryption, we get the original message, only if we use your public key. So the signature is, in a way, the message itself. It's generated differently anytime you send this message or this transaction or whatever. It's not a string that we're attaching to something. It's not something that you write down, right? It's different every single time. It's unless you're sending the exact same thing, right? Then it'll look similar. But it's generated using your private key. It is not your private key, and you can't figure out what your private key is by looking at the signature or a series of signatures or infinitely many signatures, right? It's a sort of encryption function that we're using in reverse now, where we verify that it came from the person who's holding the private key by using their public key. But that's a good question, right? So the signature itself is generated using the message, generated using your private key, unique, different every time. So here we've got a little quote on the public key from Satoshi Nakamoto. This is straight out of the Bitcoin white paper, which is good to read if you haven't read it yet. And he talks about it, and he says, the traditional banking model achieves a level of privacy by limiting access to information to the parties involved and the trusted third party. So like what that means is that the reason, so say Arthur wants to buy like porn on the dark web, and he doesn't want all of you guys to know about that and be able to go and check it. So he uses his credit card, and you can't go see his credit card statement because the bank won't let you. Now, how do we achieve that same sort of privacy on Bitcoin, right? Because if Arthur uses his Bitcoin to go and buy porn on the dark web, then that transaction is posted publicly for everyone to see. And that's no good, right? Like that's embarrassing. So the only way, because it's using his public key, we're able to see that this public key received money from Arthur, and we'd be able to track that. And Satoshi basically tells us that in order to, because we have to announce all these transactions publicly, we don't have this trusted third party, this credit card holder who's keeping all of our secrets, but we can still have privacy if we keep our public keys anonymous, right? So as long as we can't go look up someone's public key on the internet and see who has it, then we can't tell whose transactions are whose just by looking at the Bitcoin ledger. That's a lot easier said than done, right? Because in order to make a transaction, it necessitates that you distribute your public key to people. And how do we trust them in order to not publish your public key or not publish your information attached to it? That's a pretty big problem right now, right? Because like a lot of the anonymity of Bitcoin is compromised when you use the same public key for a lot of different transactions. A lot of tax agencies like the IRS and the CRA and every tax agency in the world is quite interested in knowing what people's transactions look like. And they're trying very hard to be able to trace those things back to individuals using their keys. Maybe there's a solution that we use different public keys, but it's a bit of a problem. And there are a few problems with public key encryption. So first of all, this problem, right? We have a bit of a problem with anonymity. Second of all, we have this problem of keeping the private key private, because as I said earlier, if your private key becomes public in any way, you're toast, right? Like there's no way that you can get that back off the internet. If anyone has ever seen it, they can now become you and your Bitcoin wallet and all your transactions, and they can take all that stuff. And that's not something that's easy to address. You can also lose your private key, which is something that has become pretty popular thing to talk about because Bitcoin prices went up so much so quickly. So many people realized that they had Bitcoin. And they said, well, let me just go get that private key I wrote down on a Post-it note in 2012 and make $1 million. And it's nowhere to be found, which is not there's no solution to that, right? Once you lose this private key, there's no way to ever get it back. So that's what you use a Bitcoin wallet for, hopefully, right? You store your private key in this thing, which is a little bit easier to get into. And then hopefully that you can access that in the future, but it's still a concern. So don't lose your private keys, please. And now, so now we've got the basis here. We've got signing, we've got encryption. How do we put that all together and make a transaction on the blockchain? So basically, we use a combination of techniques. So, whoops, where do we go? There we go, I think. Yeah. So basically, first of all, we have to encrypt our transaction. So we use the public key of the person that we're trying to send to in order to encrypt, right? So we take their public key, we encrypt it. Now only they can decrypt it using their private key. We've got our information. Only the person who can read it can read it. Perfect, right? But now anyone could have created this information using the public key. It's still not secure, right? Like someone else could still go make this transaction, which says that I'm sending money to someone else and send it to this individual, and that's not good. So now we need to be able to verify that this transaction came from me individually. And we use that using that signing process we just went over. So you've got your encrypted transaction, and now you sign this with your own private key, and now the transaction's complete. Because what we can do, the receiver can do now, is they can take this transaction, they can check the signature with with your public key. So they're able to see that, yes, you did sign it with your private key. That is your transaction. That is correct, right? And then they're able to use their private key to actually see what's inside of it. And that's your process. Any questions so far about that part? That's encryption. That's how it's used in the blockchain. Any discussion about that? Not yet. All right, well, then we'll move on to the second part here, consensus. So consensus is a little different from encryption, right? Like we're not using just the transactions and stuff like that. We're looking at the state of the whole blockchain, and we're trying to figure out what is the correct state. So in order for the blockchain to work, right, there has to just be one correct state where all the blocks are in a certain way and they're all consistent with each other. But the problem is that like you could generate different sequential chains from the current blockchain, and they would all look right to just an observer who doesn't know anything else, right? So they're not verifiable in and of themselves. So what we need some sort of mechanism so that the people who are using the chain can agree that they're looking at the right stuff, that they're looking at the transactions that are true and have been checked by enough people. That's what the consensus mechanism does for us, right? In traditional banking, we don't need a consensus mechanism because our consensus is that we all trust the bank and they'll do the right thing. And that's as much consensus as we need, right? And then they do whatever they want. But since blockchain is peer-to-peer and completely public, we can't trust any individual person, and we can't just trust whatever group of people has made the application. So we need to be able to distribute that trust in some way. That's where consensus comes in. And by the way that the consensus mechanisms are designed, whichever chain is the longest, has the most blocks, is going to be the correct one. And there are a couple ways of determining that and making it so that that is the case. And we're going to look at those now. So the first one, which was implemented in Bitcoin and was developed maybe a few years before Bitcoin, I think, is proof of work. Now, proof of work is still widely used, right? It's still what's used in Bitcoin. It's still what's used in Ethereum, the two biggest cryptocurrencies, I think, still. And it makes sense, but there are more systems, and we're going to go over those after this. But first of all, we'll figure out what is proof of work. So proof of work requires people who are mining on the chain, so that is validating transactions, to solve these mathematical puzzles, hashes. And what that does, like what does solving the hash do? Why does that actually prove that you should be allowed to validate transactions? Well, solving a hash is difficult, right? And it requires computing power. Your computer needs to be able to run a certain amount of cycles in order to check one hash. So if you're able to solve a lot of cycles really quickly and solve a lot of hashes, that means you have a lot of computing power. You have a powerful computer. So you're able to show the blockchain, I have, a piece of technology that is worth something, and there's value in this. And this makes our block, and this means that I get a vote. That's what essentially that means, right? If you're able to mine on the chain, you're able to change the way that the chain looks. You're getting a vote into what is the best way, like what is the correct state of the chain. So why do we need that? Why do we need to have you be able to show this thing that I have this piece of technology? And it's basically, I mention it here. I say that we determine representation because we can't use like one IP address, one vote, or one person, one vote, right? We have no way of determining if one person has one IP address, right? You could just make 1,000 IP addresses and spam Bitcoin to try and get your 51% and get your correct blockchain. You can't do that when you need to have this piece of technology to back up your vote, to back up your mining, because you can't just make more computers. Like you can, but you got to pay for them, and they're hard to make. And in the early days, right, maybe there would be more of a threat of this problem, which I go over here, that someone takes over 51% of the computing power. Because if you have 51% of the computing power, then you're able to change the state of the blockchain, right? You now control what blocks come next most of the time. So with given enough time, you're going to win out, and you're going to be able to modify the transactions, and you're going to be able to change things if you're an individual with 51% of the computing power. Now, it's very unlikely that you're going to have 51% of the computing power on an established blockchain like Ethereum or Bitcoin, because there are so many people mining on it, and there are so many people putting in so much work that you would have to be a very big entity, right? Like you would have to be like bigger than like the Chinese government in order to attack Bitcoin with a 51% attack at this point. So we can assume that it's actually quite secure, but it's not impossible, right? Especially if we start thinking about blockchain more diversely, like in smaller use cases. So when we have a smaller blockchain with smaller users, we need to understand that 51% of the computing power of those users is a lot less. And it might actually be quite easy to do a 51% attack on. So that's something that we need to keep in mind. The only thing that's keeping our blockchain secure is that there are enough honest people on it that it's very, very difficult to beat 50% of them and to have more computing power than 50% of them.
Wait, a couple of questions.
Yeah.
Like, so people mine Bitcoin because they get Bitcoin award, right? But at a certain point in time, they're just like all the Bitcoin's going to be mined. So like, what incentivizes the miners to stay on and continue to provide like that service to verify blockchain transactions?
Well, realistically, the Bitcoin never runs out, right? Because it becomes exponentially harder to mine Bitcoin. It does run out. There's a limit, right? There's a limit to how much Bitcoin, but it's better to think about that as like a mathematical limit, like lim of as Bitcoin goes to infinity is this many Bitcoins. Because as I said earlier, when we're mining, what we're doing is we're trying to find a hash, we're trying to find a string which gives us a hash with a certain number of zeros at the front of it in Bitcoin. So if you're trying to find a hash with 1 0 at the front of it, let's think for a little bit. There's 1 0, and then it doesn't matter what the rest of it is. So that means that you have one thing which has to be one way, and then 255 things that have to be one of two ways. So there's a lot of those, right? And we burn through those very quickly. Then we go 0, 1 0, 2 zeros, 3 zeros. Eventually, you have to find a hash, which is, say, to find the last Bitcoin. This is your theoretical, where we're running out of Bitcoins. We have to find a hash, which is all zeros. So it's 2 to the 256 is the probability that we find this hash, because there's 256 bits and they can be 1 or a 0. Now, how long would it take you to find something which is 1 in a 2 to the 256 is a ridiculous question. And I'd encourage you, there's actually, I don't know if I've linked them here, but there are some interesting like videos and visualizations online of like how big is the number 2 to the 256. It's so insanely large, the universe will end before we get to that Bitcoin. So the amount that you're mining diminishes very, very like up to, like the price of Bitcoin continues to go up. so that people continue to want to mine it, even when the rewards in amount of Bitcoin are cut in half. But no, like getting to the last Bitcoin isn't something that we're going to do on the blockchain.
No, that makes sense. What
the reward might get so small that people might not want to mine. It's like, yeah, technically possible, right? We're just relying on the token is worth something and worth enough for people to want to mine on it. I hope that does that answer the question?
Yeah, that makes sense. What about something like quantum computing? Like how if we just make like
Quantum
stupid
computing is
powerful
really, really scary for the blockchain.
Yeah, right. Okay.
Yeah, no, like it's entirely that quantum computing breaks blockchain entirely, but that shouldn't scare you as much as it sounds like it should, because quantum computing, if it breaks blockchain, will just like break the internet and every computing system like as we know it. Here's why, right? So basically, we think that it's possible for quantum computers to very solve these hash problems that I said were very, very different. Like you just have to sort of guess and check how on. So we don't have to worry about it. The problem with quantum superpositions to check a lot of things and essentially break like the mathematical thing on it. This is getting a little complicated. We're relying on the fact that like to check is not necessarily easy to solve. That's what we're relying on, right? It's easy to check the hash. It's not easy to solve it. It's possible that quantum computing proves that those two things are the exact same, and that because the problem is easy to check, it's easy to solve, and your blockchain will completely break. But so will all of your banking and anything that's on the internet and anything that you think is private, and anything that you've ever thought has ever been secure. So hopefully that doesn't happen soon. And if it does, hopefully someone smarter than me figures out a way to fix it. But I'd advise you guys not to worry about that. All right. Yeah, so we already talked about this. Basically, the consensus chain is the longest chain because that's the one which has the most work into it, right? That's the one that the most miners have been working on for the longest time. If you're an attacker, you're not going to be able to make a longer chain, right? Because unless you have more than 51% of the power, because the people with 51% will be able to extend the chain before you, because they'll be able to find the hash before you. Easy enough. Proof of stake. So proof of stake is very interesting. And it, I think, seems like a better system to me. Some people argue that it's not. And it addresses a lot of the concerns that people have about proof of work. So you might have heard, you know, Elon Musk and Bill Gates, you know, talking about how Bitcoin is bad because it's bad for the environment. Because like in order to solve all these hashes, you need to use all this power, right? And if China's using all this power that they've generated from coal mining and it's not from renewable resources, that's pretty bad for the environment, especially because it's not doing anything, right? Like when we find all these hashes that are wrong, is nothing. It's just wasted computational power that could have gone to solve some really cool problems. Ideally, our system doesn't do that. And now, if that's actually as big of a concern as those people have made it out to be, is up for debate, right? Because like we got to consider that if this is an alternative to traditional banking systems have a lot of, you know, environmental overhead as well. And like how much electricity really is it on a worldwide scale when we compare it to something like that? But realistically, like it is a problem, right? It is something to think about. And how does proof of stake address that, right? So now we don't want to use like problem solving capability as our point for what makes someone allowed to validate the blockchain, because that's bad for the environment or for whatever, right? So the way proof of stake works, which is what is used on Cardano, and Ethereum is talking about moving to proof of stake, and they've been talking about it for a long time. I think it's possible to stake Ethereum still in some way. I don't really understand how it works. I think it's like a Ethereum 2.0 thing. Basically, sorry, getting sidetracked. Proof of stake, instead of using your technological capital, so your processor chip or your GPU is your capital that we were using in proof of work. In proof of stake, it's more direct. It's your Ethereum or your Cardano is your stake. That's your proof. What you do is you put this up, this thing, and in order to run, the way it works is that you have to run a node to validate, right? To have a node, you have to have a certain amount of the currency. So Ethereum's projection for when they move to proof of stake in the indefinite future is that you'll have to have 32 Ethereum to run a validation node. It's kind of a lot of money right now, right? I don't know how many of you have 32 Ethereum, but if you'd like to send some my way, that would be great. Basically, the point is that if you have this amount of capital, there's some degree of trust we can put in you, right? Because you're not able to just generate this from nowhere, right? You have to have it. So that means that no individual can just have unlimited stake in the chain. And there's also this interesting property that once 51% of someone controls the currency, if you control 51% of the currency, that can actually affect the value of the currency itself, 51% attack that we talked about with proof of work. You can also argue that it's more fair than a proof of work system. It might not seem like that at first because we're just using money, right? And we say, well, money is whatever, right? It's not that fair to say if someone has more money, they get more say. But it might actually be more fair than proof of work. And the reason is economies of scale for like processing technology. So the way that Bitcoin is currently mined, right, is the only way you can actually really get any is if you have these designated computers that are specially designed with special types of processors called NASCII. And they're designed such that the only thing that they do is run these hash functions. And now they need to be that way because it's so hard to mine Bitcoin. Like, you know, in 2012, you could mine it on a background process on your Pentium core on your laptop. It doesn't work anymore. You won't ever make any money. You need to have these fancy designated computers. And when you want to build a lot of these computers, you can actually take advantage of scale, right? You're able to say, it's much cheaper for me to build 10 million ASCIIs than it is for me to build just one, like it's cheaper per unit. This means that I can actually leverage my higher economical stake into an even higher technological stake. And I'm able to get even more mining power than I had by the dollar, if that makes any sense, right? Like someone who has $1 to stake gets equal rewards on that dollar as someone who has $1 million. Like, I mean, the person who has $1 million gets more reward, but it's scaled with the amount that they have put in. So when we get rid of that technological element, then your amount of stake in the system only scales like linearly with your amount of money, which is arguably more fair. So that's an interesting thing. And I think that's the end of my slides. But if anyone has questions, I don't think I was terribly clear about everything. I'd be happy to answer some.
Yeah. Can you just quickly compare like the pros and cons between proof of work and proof of stake? Like, I think that stuff is really interesting.
Yeah, that's definitely a really good thing to talk about. And like, it's interesting because Ethereum is in this process of migrating between the two. So what's good about proof of work? So proof of work is, well, first of all, like it's easy to understand, right? Like you have to hash these functions. Once you find the right one, that's your proof. If you have a lot of them, it's easier to find them. And it being sort of easier to trust is a very good thing for blockchain. But it has, you know, these problems that I addressed earlier. So it's got cons that are like, it can't, it doesn't scale well environmentally because you have to, like I was saying, it gets exponentially harder. It becomes very, very difficult to mine Bitcoin. Computing power only scales linearly with time, we think. So you're going to have more and more processors, and you're going to have to be pumping more and more electricity into them. That's not good for the environment, and it just seems wasteful. Like it doesn't, even if we don't care about the environment, like all those computers could be doing something else besides just like ensuring that our currency works. So that's not that good, but it's pretty good at giving everyone a say, right? Especially in the early days, proof of work was actually, I think, made a lot of sense when Bitcoin came out, because you were able to mine on your laptop and you were able to mine on your GPU and, you know, actually see returns and see that you were participating in the blockchain. And that's kind of nice, right? And that's good. And that's what we want for the blockchain. We want people to be able to join and see that it actually works for them and that they're a part of the system. And that's the whole point of peer-to-peer. But we've kind of lost that now. Like you can join a mining pool or whatever, which is actually something I didn't talk about. Pools are an interesting way that we can distribute the power, especially with stake too. So I mentioned in, sorry, I should address that for proof of stake because that's actually very important. I told you need a lot of currency to run this node, right? So what if I only have a little currency and I want to stake it and make money on it? Well, you can still do that, right? You just need to be a part of a group of people contributing to that stake. So Cardano does it. I have some Cardano staked and I make money on it by doing nothing. It's great. So basically what happens is you have someone has some stake, they become the validator, they operate the node, they do everything, they receive the rewards, but they don't have quite enough stake to run the whole node themselves. So what you can do is you can send them some of your money, they hold on to it, they use that as their stake, and you get a piece of their rewards in return, which is great. The same thing actually works for mining, right? Like if you can, I don't know if I think this might be too complicated to try and explain right now. There are a couple of mining pools, right? Like that you can join as a miner and work with other miners in order to towards mining blocks and get distributed a piece of the reward. It's still not that practical if you don't have that much computing power. But proof of work worked great back in the day because you're able to, you know, earn rewards on your computer, see it working. Now it's getting a little bit ridiculous. So what kind of concerns does proof of stake address? Proof of stake has these pros that we talked about of being still trustable, right? Like we can still say that money is a valid reason to give someone a vote, just as valid as computing power. For that reason I addressed, maybe even more valid. Doesn't have all these externalities to the environment that we should be concerned about. And potentially is more secure because computing, like I said, you know, with quantum computing and all this stuff, it's like we guess that computing power scales linearly with time, but like we really don't know. It's very possible that someone could develop, you know, a faster way to run hash functions and not tell anyone about it and have 51% of the network, right? Like, and that's not probably going to happen, but it could. And those are the kind of concerns that we need to think about when we're designing the blockchain. Proof of stake doesn't so much have that, right? Because you can't just generate more of the cryptocurrency. You need to get it from having it staked. So there's no concerns about some possibility of just coming in with all this extra computing power and taking over 51%. But proof of stake is still vulnerable to a 51% attack, right? If you have 51%, the currency, you've got the network compromised. It's a big problem. Does that give you a bit of an overview there?
Yeah, no, that makes sense.
All right, great. Any more questions from anyone else? Arthur's giving me all the questions. No? All right. So I think that covers everything I wanted to say. And if no one else has any questions, then I think the next lecture isn't next week, but the week after that. And I don't actually remember what the topic of it is.
It's on mining.
It's on mining. Oh, so we're going to get to learn a little bit more of what I was just talking about consensus. Now that we know how the miners come together, you'll be able to see how does the mining actually work individually. Hopefully you'll remember a little bit from this lecture. All right. So I guess that's about it. Thanks for coming, guys.
Yeah, thanks.
Liam.